the journeys to work in the Cambridge sub-region, but from perspective. Yes, so this has, well, we have two authors here, Timea Nocta and Jennifer Schooling, both sit in the audience, and I present on their behalf. I'm going to talk about three things. First is a very brief introduction in terms of the where does this digital twin concept come from? What's the right? Yeah, and the whole development that's up to date in the UK context. And then I will talk about three propositions. In terms of how we get to these three propositions, these are all question-driven. So in terms of how I'm going to present this, I'm going to show one first, and then proposition, question, proposition. And these are really sort of high-level theoretical content, but this part is quite empirical. This is to show you a case study of journeys to work in this region. So the concept of digital twin, well, I think appeared first in the manufacturing industry in about 2004. In the UK context specifically, the revival of this concept beyond the engineering world really started from this report. So this is the data for the public good by the National Infrastructure Commission. So the National Infrastructure Commission in 2017 recommends national digital twin for the UK infrastructure. And they have listed a few high-level benefits of having this national digital twin. Following that, the Digital Framework Task Group has been established, led by Mark Enzer from Watts McDonald. Jennifer also sits in the DFTG. This DFTG is hosted at the Centre for Digital Great Britain. So by the end of last year, the DFTG published the Gemini Principles for, in terms of guiding the development of So far, that's the background of digital twin, particularly in the UK context. We touched on this concept, and then we found all sorts of questions, problems. And these particularly three propositions are driven by the questions that we have sort of encountered when we try to communicate what we are trying to do here in Cambridge to other academics and partners from the industry and the local government. I also note that in the paper, we have more than three propositions. So these are the three things that I really want to highlight in this presentation. First question, given the origin of digital twin in the manufacturing world, from manufacturing to cities, is this a simple transition of scale? So this is I think this is a steam engine, a steam turbine. So this is a pretty established model, I would say, in engineering terms. And that is a Google image showing that the possible a digital twin for the city, or part of the city. How we move from digital twin for engineering projects to that level of spatial scale. Well, I'm from a sort of a planning perspective, and the proposition really, so just unverified, is that the upscaling from an engineering digital twin to a city level digital twin is not straightforward. In academic terms, this might not be totally helpful. So when we talk about the city level digital twin, what are we actually talking about? We don't know quite yet, to be honest. But there are some key dimensions that we think are quite important. So when we talk about a city-level digital twin, we need to specify these things first. First of all, the policy domain and the range of stakeholders that involved or being targeted of this digital twin. Essentially, this raises the question of this twin is about what and for whom. And second is this locational context. This is to say whether this is a city growing or declining. It's a small city or it's a metropolitan area. Is it a city in UK or is it a city in China? And the last one is the spatial temporal scale. Of course, this is real time and how real time, the granularity of the model. And these three dimensions are not independent from each other, so they are somehow correlated. Second question. Well, if you got time to read that report, you somehow feel that if we get to that point, say we have a quite established and working national digital twin, then all problems will be solved. But the question that we have found is that if we can't build the better cities, why the digital twin can? And well, most people use the Terminator picture, but I use a more up-to-date version. So this second proposition, in terms of the intellectual relationship between a digital twin and the civil society, really, we believe that the digital twin development is a progressive process. The digital twin and the social system that use it must co-involve with each other. So on the one hand, our existing knowledge in terms of cities and infrastructure planning defines how well we can develop and use this tool. But on the other hand, I think the AlphaGo for cities may appear. I don't know how long, what's the time scale of that, but if the artificial intelligence becomes really powerful, then it can actually complement intelligence, new knowledge about cities. So that is really the tipping point where digital twin may be a game changer. But I think my personal view on that is that we are not there yet. So for now, doing academic research into a city really to build a new body of knowledge so that this drive better urban simulations, not expecting digital twin can automatically solve all the problems for us. Third question. We try to present our empirical work in Cambridge to all sorts of people, and one common question is that do you use real-time data in your model? We do use, but only for a small portion. So then people say, without real-time data, this is not a digital twin. So the question is, how real-time is real-time? I can provide you these two examples showing what's the problem. This shows the population growth from 1800 to 2011 for London. Line is Great London, Inner London, and Outer London. And if you calculate the equivalent annual population growth for Great London for the past 200 years, that's about 1% per year. Okay. We can also do an interesting exercise to calculate the percentage growth per day. That leads to about 0.003%. So that is presumably the real time of population change. And then we have this data. Well, this is not my work. I got this from a researcher from UCL. It's showing the passenger flow at Leicester Square station by a 15 minutes interval. So I think if we talk about real time, it involves quite different definition between these two cases. So this is our proposition. Real time is a relative. The temporal scale of the digital twin should reflect the rate of change of the subject system processing reality. So it's all about, it means that it's not necessarily that the more data, the better, or the more real time, the better. It has to fit the purpose. If a transport investment appraisal takes 2 or even 5 years to pass, and then I would say quarterly data or monthly data could be claimed as real time, not second by second. So that depends on really what you're trying to achieve by that model. Another argument relates to that one, is because we'll talk about the temporal scale, and in terms of the spatial one, a digital twin does not necessarily mirror the city in geometric terms. We somehow get this, or found this, there's a tendency among cities that if they want to engage with this digital twin agenda, the first thing they are going to do is to have a 3D model with a very high level of detail. But we're saying that, well, again, depends on the purpose. You don't really need a 3D model for anything. And so far, that's the high-level, non-empirical findings. And then we talk about this case study, which is trying to develop a digital twin prototype for understanding journeys to work in the Cambridge sub-region. This broadly shows the study area. The whole area is called a Great Cambridge and Great Partnership Local Enterprise Partnership, which includes the Peterborough, the Cambridgeshire and the Peterborough Combined Authority area. The total population for this whole area in 2011 is about 1.5 million, and the population in Cambridge City is about 120,000 by the year of 2000. So what's this digital twin about? Called the three key dimensions in my early slides. So I do stick to my words. I'm going to introduce the digital twin using that 3 key dimensions. So in terms of policy domain and stakeholders, this digital twin trying to address the cross-cutting issue between transport, such as congestion issue, air quality, and the energy infrastructure. What sits in between is the future use of cars, particularly the combustion engine cars. So that's what we are trying to model here. In terms of locational context, Cambridge area sees a quite strong momentum of growth. So it's one of the fast-growing city regions in the UK. And the sort of higher level policy goal for the whole region is trying to sustain that growth. Okay. In terms of the spatial and temporal scale, so this model is not about managing the traffic flow in real time. So this is more about strategic planning. So we look at 2031, 2051. So it's really long term. In terms of the workflow, so this is actually the digital twin model I talk about. It has 2 components. First is interacted. First is the residence location choice, and it's the model choice. This is quite similar to the conventional 4-step model. We train the model, the journeys to data, particularly using the 2001-2011 census, and then we generate a series of scenarios based on these inputs. So the future employment and population projection, the future land use and transport plan, so where you put new houses, where you put new roads, and also the assumptions on the work and travel. What does it mean? I will show you shortly. And the output of the model, travel volume by origin and destination, and method of travel, so how you travel. We have 4 endogenous modes. So we have driving, we have bus, we have cycling, and we have walking. But we don't model the use of train endogenously. And I will demonstrate the use of what the model can do using 2 illustrative scenarios. I use illustrative. Actually, these 2 scenarios are quite crude. So the intention is that this is not to produce a sort of a definite answer to these big questions. It's just to show that how model can do, and we want to use this as sort of a starting point to engage with a wide range of people to see how they think of this new approach. Scenario 1 about telewalking. The question is about to test how telewalking may impact future travel demand for commuting. And second scenario, the electrical vehicle charging demand. The key variable here is the spatial development strategy. So how different spatial development strategies may affect the distribution of electrical vehicle charging demand. First scenario, telewalking. This scenario builds on very strong assumptions. One of those is what jobs are working in the future. So we go through, breakdown of the national statistics socioeconomic classification, trying to figure out what jobs can be done while teleworking. This is our assumptions, really. So we say that medium to high skill jobs, being self-employed, and requiring no access to machinery would make you sort of more possible to do teleworking than other jobs. And these are sort of the percentage share we assume. If we apply this scheme to the employment profile of this region, by 2051, about 14% of jobs could be done while teleworking. And then we put these jobs through the model, and the model tells you how these jobs, the residence location choice of these workers, and also how they travel, whether they will use car or not. So the polygons, the color of the polygon shows the possible reduction of commuters at the home place. So, for example, if you live in Camborne, probably about 1,500 people do not have to commute to your workplace on a daily basis. And this line shows you the workplace, so basically where you travel to, by car particularly. We do see quite lots of reduction within the city boundary, but we also see middle range journeys that can see a huge reduction. Actually, here is that the magnitude of change is significant. So this addresses the uncertainty in terms of how we model the future commuting demand, which is not properly addressed in the current transport models. But second is that we also provide us the caveats. This is where we want to do further research. For example, the literature says that if you reduce the time for commuting, then there will be increase of non-commuting travels, for which we haven't addressed here. Second is the change of residence location. So if I don't have to commute 5 days per week, I only do 2 days. Possibly I can live even further away from my workplace. We can turn this on in the model, but for this map particularly, that one is turned off. And second is that we haven't double-checked whether places in this area have that necessary connectivity in terms of fiber broadband or 5G sort of things, so that they can technically do teleworking. Second scenario is about the electrical vehicle charging demand. Like I said, the key variable here is not the type of vehicles they use. It's about how the spatial strategy may affect that. So we compare 3 scenarios. First is this business as usual. So we look back to the past 35 years and extrapolate the future. And then the densification scenario, if we concentrate all that growth within the city boundary, do not allow to take up any sort of greenbelt land. And third scenario is called fringe growth. We do allow some of the land to be released from the greenbelt. How would that affect the EV charging demand? Again, these are very strong assumptions. We don't consider the different types, just assuming that all cars commuting to Cambridge in 2051 are electrical vehicles, and they all need to be charged. And we also assume a uniform electricity intensity for the car by mileage. So this is the baseline. The map here shows that if all cars have to be charged at the workplace, so you don't charge your car at your home place, you drive to work and charge at your office. And that is the opposite. If everyone charges their car at the home, they don't charge at the workplace. You see that these two are quite different patterns. And this is the densification. So if we concentrate all the employment growth within the city boundary, and that's the difference. One implication is that if this level of demand is not manageable in the short term, through sort of a pricing policy, you can actually nudge people not charging at the workplace, so you can spread the demand. But again, this means that the people working in energy and transport, they have to work together. And this is the fringe growth. You see that well because people live and work in the same place, so they probably you don't see too much difference. My last slide. Well, these our sort of findings are still evolving, so I'm quite open for question. A city-level digital twin is not a one-size-fits-all solution that can be just simply deployed without context. This means that if a new model for Cambridge works in terms of solving congestion or air pollution, doesn't mean that it may work for London. It probably will not. So, in terms of how we get there is that we have to co-develop this with the policymakers, with the citizens. A major challenge here is that back loop for learning and adaptation. The problem of conventional urban modeling is that we have a quite good model. We'll produce model report, and that's it. So there's no learning, no feedback loop. In technical terms, this means validating the model, but also in governance terms, this is how you improve your policy making to make a better use of this evidence. At a certain point, we do think that this city-level digital twin can serve as an object in terms of bridging the disciplinary and the professional silos. So this enables people from different backgrounds to work together, which is a big enabler. Last point, in the engineering world, people think digital twin can do this system-wide optimization. But if we apply this concept to cities, optimizing for the whole city